So in this video, we want to get a feel for where the quotient rule for derivatives come from. I mean, it should be clear that the rule that we get for finding the derivative of a quotient or ratio of two functions isn't on its surface intuitive at all. And we should be asking the question as users of math, why is it the case that we can't just take the quotient of the derivatives? Why is it not this simple? And so what we want to do is look at where this comes from. So it's going to be similar to the derivation for the product rule for derivatives. Let's to make things a little bit simpler to begin with, take a ratio or quotient of two functions and give it a name. Call it q of x for quotient. So if you were going to find the derivative of q of x, you would use the definition of the derivative, which is just the limit of the difference quotient as h goes to 0. So the derivative of q is the limit of, as h goes to 0, of the difference quotient for the function q. But q is just a ratio of two functions. So if I'm replacing x plus h into the function q, I'm actually putting x plus h into this ratio. And if I'm subtracting q of x right here, I'm really just subtracting f of x over g of x. So we can make a couple substitutions. We can replace q with its ratio, f over g, and where we see the x plus h, we pop it into the f function and the g function. And we replace q of x here with f of x over g of x. And anytime we have a subtraction of ratios going on, it kind of screams at us that we should probably investigate finding a common denominator and seeing what that looks like. So to get a common denominator here, we would just be multiplying this term by g of x over g of x, and this would be multiplied by g of x plus h over g of x plus h. And we know if we're dividing everything up here by an h, that's the same as multiplying by the reciprocal of h. So that said, that moves you to the next line. Here, all that happened on this line is we found a common denominator. I have my f of x plus h times my g of x minus my f of x times my g of x plus h. My common denominator was g of x times g of x plus h, but this division by h was the same as multiplying by a 1 over h, which I can either decide to tuck in underneath with the other stuff, or I can leave pulled out front. Once I get it here, it really is a matter of trying to get it to play out the same way that we did in the product rule. I know that to get the derivative of f, I need something that looks like f of x plus h minus f of x, and I'm going to need it over h, so I can take the limit as h goes to 0 and get the derivative. So we look at the first two terms here and we say, what can we subtract from these two terms to move it in the direction of getting it minus f of x, minus f of x? And the answer would be, well, I would need to subtract f of x here, but I've got to be able to get this g of x off of the f of x plus h. So I could subtract minus f of x g of x, which would allow me to factor off the g of x and leave me with an f of x plus h minus f of x, which starts moving me towards getting the derivative notation. But I can't just arbitrarily subtract, so I would need to add on the same thing. I would need to add on an f of x, g of x term here, or I will have changed the value of the numerator. So on the next line, that's all we've done. We've subtracted from f of x plus h g of x the thing that we need to get this difference quotient thing going on, and I've added the same amount on the far end, so the net result is we're adding a 0. We subtract it, we add the same thing, we get a 0. So we've changed how it looks, but not what it is, not its value. So this statement is equivalent to the previous statement. And so the next step is going to be, let's factor the g of x off. Let's think of the h as being times a 1 over h, so that we can distribute it into the numerator if we need to. And here we've got an f of x showing up twice, so we're going to factor off a minus f of x, which is actually going to be nice. It's going to leave us with the g of x plus h minus g of x plus h minus g of x, which if we can get it over h, and take the limit, that's going to be the derivative of g. So that's the next move. The next move is factor. So factor that g of x off, which happened here, which leaves behind the difference between those two, the f of x plus h and the f of x. And then factor the f of x off here, which happened right there. And then take this 1 over h and distribute it into each of the two terms in the numerator, which will give us an h down in the denominator position. And now once we get it looking like this, it's that homework 2 situation again, where it was analytic or algebraic calculation of limits. We know that if we want the limit of a ratio, we can take the ratio of the limits as long as we don't wind up dividing by 0. So in the next line, we just bring our limiting notation into the denominator and into the numerator, doing a couple steps at once. But this limit right here, you want to recognize that's the limit as h goes to 0 of the difference quotient. That's the derivative of f. And the limit as h goes to 0 of the difference quotient applied to the function g is just g prime. And if we're taking the limit as h goes to 0 of g of x plus h, we'll just replace that h with a 0 in the end. We'll get g of x times g of x, which is just going to give us a g of x squared. So we wind up with the derivative of f times g right here, minus the function f times the derivative of g here, all over the square of g. So again, it falls out of applying the definition of the derivative.